Hello. So in this video, we're going to talk about related rates. And we are just going to think of related rates as being essentially implicit differentiation applied to word problems. So you can count yourselves lucky. In the regular calculus sequence, these problems get pretty contorted. Whereas in this class, we will limit ourselves to problems like this. The cost in dollars of manufacturing X high-quality computer laser printers is given by C of X equals 15 times X to the 4/3 plus 15 times X to the 2/3 plus 600,000. Currently, the level of production is 1,728 printers, but that level is increasing at a rate of 350 printers each month. Find the rate at which the cost is increasing each month. I say implicit differentiation. Maybe it would be more accurate to say that we use the same trick that we use when we do implicit differentiation, which is that we treat one variable as a function of another variable, even though you don't see it written down in the problem. What I'm trying to get across with that statement, we had x squared plus y squared equals 1. And we don't see any function notation here. We just see two variables, x and y. But when we did implicit differentiation, we treated y as a function of x. And because we treated y as a function of x, when we differentiated, we needed to use the general power. Well, something very similar is going on with this example. We're looking at C of x equals 15x to the 4/3 plus 15x to the 2/3 plus 600,000. Okay, so if we wanted to take the derivative, we could do this. We could find C prime of x using the general power rule, but there's a hitch, which is that x depends on time, right? Because let me see if I can find this once more. Because of these two lines down here. At the current time, we are producing 1,728 printers, but that is increasing with time. That is increasing at a rate of 350 printers per month. So X depends on, and furthermore, the derivative we want is a derivative of time. We want to find the rate at which the cost is increasing per month. I said we could take this derivative, but if we take this derivative, it is not dollars per month. it's something else. It's dollars per printer. So hiding in this equation is the fact that x is itself a function. X depends on time. X is a function of time. So, what's that mean? Well, it means that if we want to find dc over dt, we'll differentiate stuff. We'll differentiate this kind of polynomial-looking expression. But because x is a function of time and we're differentiating with respect to time, we're going to need the general power rule here, just as we did in the implicit differentiation problem. So 15, the constant remains. The 4/3 comes down. We reduce it by 1. 4/3 minus 1 is 1/3. But we're using the general power rule, and that gives us a dx dt term. Likewise, with the 2/3, the 2/3 comes down. 2/3 minus 1 is negative 1/3. But we're differentiating with respect to time, and x is a function of time. We have a function raised to a power. We're taking the derivative. The general power rule gives us a dx dt. And then the derivative of 600,000 is still just 0. So I'm not going to simplify this terribly. 15 times 4 is 60. 60 divided by 3 is 20. X to the 1/3 dx dt plus 15 times 2 is 30 divided by 3 is 10. X to the negative 1/3 dx dt. And our answer, our time derivative, has x's in it, and it has dx's in it. And both of these are given by the problem. X is 1,728. Dx dt is the rate of change. Positive 350 printers per month. And now we can just take the x and we can plug it in, and we can take the dx dt and we can plug it in. Let me do that on my calculator. Let me pause this. The cost is increasing at a rate of $84,291.67 per months. And that, at its heart, is a related rates problem. And I mean, it's called related rates because we want a rate. We want the derivative of cost with respect to time. And the rate that we want depends on another rate, the derivative of x with respect to t.